Is it on? Yes. So, welcome to the second session of today. Before we start, I was asked to make a couple of announcements. First is that the audience that you see here is only a small fraction of the actual audience of this conference. You're being watched online, so you better watch what you're talking about, especially if you're a mathematician who is using a work of physicists and tries to ignore it, as Isaac Newton. And the second announcement is that the previous talks are already online, so you can check them on the website. And now I'm happy to welcome Olivier Schiffmann, who will talk about the Cohomological Hall algebras and something else, and Katz polynomials. Thank you.
First of all, thank you very much for the invitation. It's the first time I come to this place. Definitely the first time I talk in a physics conference. And definitely I tried to put some physics term, not too many. And definitely I made mistakes. Okay, so I want to talk about some series of works, let's say, joint with Tristan Bozek, Francesco Sala, and Eric Vassereau. And let me start with some heuristics about the kind of things that we do. We consider the following way of constructing some operators in homology. So suppose we have two smooth algebraic variety, some closed subvariety in their product, and let us assume that there's a projection from Z to one copy which is proper. Then using the now classical convolution operator, we can define a map from the homology of M tensor the homology of Z to the homology of M prime, given using this formula. This is a very standard way of constructing operators in homology. It appears in many, many places. And here in this talk, I want to focus on one particular type of such correspondences, which arises in the following situation. Suppose M is M prime, and it's some moduli space of, let us say, stable objects. And usually you have to consider objects with some extra structure. This is heuristics. It's written on the top line. And so it's a moduli space of some stable objects with extra structure in some category A, abelian category. And the subvariety Z that you consider is some kind of incidence variety. So it's the set of pairs, O prime, of objects in your category, such that one is included in the other one. Okay. Now we can also consider the moduli stack of objects in A. So now we're not worrying about taking stable objects or having some nice geometric properties of our moduli space. We consider the full stack of objects. And then there's a map. I said this is heuristics, which sends this incidence variety to that moduli stack simply by taking the pair of objects and assigning to them the quotient of the big one by the small one. And therefore, we can pull back classes, let's say, from that stack to Z. And in this way, we get a map from the homology of the moduli space of stable objects with extra structure, tensor the homology of the moduli stack of object to the homology of the moduli space of stable objects. Okay, this is just specializing the previous construction to classes which are pulled back from this moduli stack of objects. Okay, now this is where we come to the notion of a cohomological Hall algebra, still heuristics. I say that this map here, this equation 1, can be seen as the action of a certain algebra on the homology of the moduli space of stable objects. And how we do this, we consider these Hecke correspondences. These appear everywhere. They appeared in Hiraku's talk this morning. So what is the Hecke correspondence? It's just the same thing as before, but now inside the stack of objects. And then we have these projection maps. And then we have the projection maps, Q and P, which now send a pair of objects to the quotient and the subobject, respectively, and to the overobject, the big object. Okay, and this kind of diagrams allow us, in dream world, to define some algebra structure on the homology of the stack. Okay, just by pull back and push forward, as usual. And this is in red. It means it's a danger here. This is just in nice cases that this algebra structure will define, will be compatible with the action on the moduli space of your stable objects. Right? You have some checks to make sure. And one way to phrase it, this has been phrased by many people before, including Kontsevich and Zeubelmann. The cohomological Hall algebra of the moduli stack of objects in your category acts on the cohomology or the homology, whatever, of the moduli space of stable objects with some extra conditions in your category. Okay, this is all very, very abstract, and it's maybe a nice way to think about this construction, but you shouldn't take it too seriously. And just as a first attempt to wake up some people who already have fallen asleep with all these diagrams, I believe, and I'm probably wrong to say that this is one version, one example of an algebra of BPS states. Wrong? Kind of wrong. Okay, let's move to the next slide. Okay, let's do one concrete example of all this crazy machinery. This is in relevance 2. This is the other place where I make a fool of myself. Aldai Gayoto Tachikawa correspondence in Susai, n equal 2, UR gauge theory. And this is the danger, pure without matter. Maybe it's not the right word, but it's one very simple case of this AGT correspondence. And in this case, I would say the category underlying is coherent sheaves on C2, simplest surface. The moduli space of objects, stable objects, in this case it's not even stable, but with some extra condition, is this moduli space of instantons, so torsion-free coherent sheaves on P2, framed at infinity, and it has lots of connected components. This is the moduli space of rank R instantons, and maybe slightly less familiar to people working in this AGT. What is the corresponding stack? Well, it's how are you going to go from one, suppose you have an inclusion of two such torsion-free coherent sheaves, then you can easily see that the ratio between the two is a coherent sheaf, but it has to be on C2, but it has to be of dimension 0, supported at a finite set of points. And so we can view this in terms of stack as, well, disjoint union over all possible dimensions of the stack of pairs, the commuting variety. So pairs of matrices such that their commutator is 0, and then you take the quotient by the group GLD. This is the moduli stack of 0-dimensional sheaves on C2. This doesn't work anymore. Okay, so this is the relevant object so that we want to consider the cohomological Hall algebra of that guy. And we can pull in some equivariant parameters in our homology because there's the 2 torus which acts on C2, and therefore it acts on all the spaces that we consider. And so we can consider this cohomological Hall algebra, which is defined like this. As a vector space, it is the equivariant, T-equivariant homology, Borel-Mon homology of this commuting stack. And there is an associative algebra structure on this, which is not as easily defined as the previous slides suggest, but this is why it was called heuristics. But anyway, there is a way to define a natural associative algebra structure on this space C. And so what Vasro and I proved a few years ago was that this COHA is, in this case, isomorphic to a very nice object, which is now called the Yangian of GL1 hat. And then more precisely, it is the positive half of the Yangian of GL1 hat. And it acts nicely, faithfully, and cyclically on this homology of the moduli space of instantons. So one nice thing that I like about this COHA is, well, the bad thing about the COHA is that these spaces are singular. But the nice thing about the COHA is once you make the hard work, then you have the same algebra acting for all values of R in this case, all rank R. You can, once you have done the job for R equals 1, the Hilbert scheme of points on C2, then you can translate a lot of information directly to this action on the moduli space of rank R framed sheaves. And for some reasons, it is better to consider slightly different correspondences. So you can consider, instead of coherent sheaves on C2 of dimension 0, you can fix the dimension, the support, sorry, of your coherent sheaf to be on a certain curve so that you get a Lagrangian analog of these varieties. These are better behaved, as we will see. And well, all this formalism can be made to work if you have the right hypothesis, the right techniques. So you can do everything with K-theory, Chow groups, and you can look at the papers of Yang and Zhao, where they do this for oriented cobordism theory or something like that. Okay, I really have to say that Molik and Okunkov constructed an action of the same Yangian by a completely different method, using stable envelopes, R matrix. So their approach is more gauged towards understanding the R matrix. And, well, it is a recurrent theme in this talk that this COHA is some kind of a rival to this Molik-Okunkov algebra, and we would love to relate the two, but at the moment we don't have a very precise, nice theorems to say that. So we will just focus on this COHA here. Okay, so this moduli space of instantons was one particular example of a Nakajima quiver variety. So let us try to generalize what we did before to arbitrary Nakajima quiver varieties. And here I really want Q to be arbitrary, by which I mean it is allowed to have, of course, multiple arrows, but I also want oriented cycles, but I also want to allow loops. And my favorite quiver here is going to be this SG quiver, which is related to this character variety, genus G character variety, and these things by the work of, say, Hausel and Letellier, Rodriguez-Villegas. So this is my favorite quiver for this talk. And a lot of things that I will say are analogs of results that have been obtained by previous people in the case when quivers didn't carry these kind of edge loops. But this is really the point here. Okay, so regardless of whether you have edge loops or not, this theory of Nakajima quiver variety exists. And let me remind, I'm sure this is a good audience for this, that to a pair of dimension vectors for my quiver, I have a triple of a smooth symplectic quasi-projective variety, affine singular variety, and a projective and semi-small map from the smooth guy to the singular guy, which is the desingularization. Okay, and if you take Q as S1, this Jordan quiver, then you will recover the moduli space of instantons, rank W instantons. And you have all the connected components are given by this other dimension vector phi. And, well, the way I like to think about Nakajima quiver varieties is the following. I like to think of them a bit like framed torsion-free sheaves on P2, except that now we have quivers. So you can consider the moduli space, let's not try to make this very precise, of framed V-dimensional representations of your quiver. So you don't only consider representation of your quiver of dimension V, but you also give as a data a framing, which is a map from some projective object determined by this dimension vector W to M. And then you take the cotangent bundle to that moduli space. And you can think, this is the first approximation, of course, it's not true, that this Nakajima quiver varieties is the cotangent bundle to that. This is one way of viewing these symplectic varieties. And so what is the relevant COHA? We should consider pairs of framed, or say in the cotangent situation, pairs of framed representations and assume one is included in the other and look at what we would get as a quotient. And here is what we get. We have to, because we are working in the cotangent situation, we have to double the quiver. So I replace every arrow by a pair of arrows going in opposite directions. And I consider the path algebra of that doubled quiver. And so the algebra generated by path, and the multiplication is just concatenation of paths. And I take the quotient of this path algebra by these kind of relations. Sum of a gamma of x gamma star. So every arrow is paired up with the dual arrow, and we take the commutator. And this is the so-called pre-projective algebra of Q. And you can think that morally, the moduli space of representation of this pre-projective algebra is the cotangent to the moduli space of representation of your original quiver. So this is just like the representation of your quiver, except in this cotangent situation. Now you notice it's not smooth anymore. This is a singular guy in general. Okay, which makes things a lot harder. So there's a big torus acting here. For instance, we can take the maximal torus that I can see, which is associated to every edge in your doubled quiver, and you need some relations between you need to take a subtorus so that it preserves this moment map equation. And let's just look at one example. If you take Q as this SG quiver, then you see that you get something interesting, because this space here looks like, say, the tangent space to the moduli space of local systems of your genus G curve. And you take the tangent space around the trivial local system. This is some kind of tangent space of identity of the character variety, genus G character variety. And you have this G plus one-dimensional torus acting in this case. And if you consider S1, which is this Jordan quiver case, then you get exactly C of X1, X2, X1, Y1, which is your space of regular functions on C2. So this is exactly what we had before in the case of the Jordan quiver. Okay, so here is the theorem. This is, once you've done it for the Jordan quiver, it's easy to generalize for an arbitrary quiver. For GLR. So once you've done it for S1, it's easy to do it for any quiver, and you get an associative algebra structure on the direct sum of homologies of your stack of objects in pre-projective algebra, and it acts on the homology of these Nakajima quiver varieties. So, of course, this is not the first guy that acts on the homology of Nakajima quiver varieties. So Nakajima himself constructed actions on the K-theory, and later Varagnolo constructed action on the homology. And our action is, gets in particular their actions, but we can, using this formalism, we can hope to get more. This is the main point. This cohomological Hall algebra is built so that it will give you all possible operators on these Nakajima quiver variety, which factor through these Hecke correspondences. So any operator that you can define that is factoring through some Hecke correspondence is in this COHA, essentially by definition. Nothing deep here. Okay, so before I state some results about this COHA, so now the aim is what? Is to understand this COHA as well as possible. We saw that in the case of the Jordan quiver, we already have a very interesting object, which is this Yangian of GL1 hat. And right, so this is the aim, understand this COHA. And a slightly better picture, or at least easier for us, is when we replace these correspondences by the Lagrangian correspondences. So we define a representation of the pre-projective algebra to be semi-nilpotent if there exists I-graded, everything lives over the vertices of the quiver. So V, for instance, and W are all I-graded spaces, and C power V is also an I-graded space. And we can consider partial, this is important not to miss this word, it's not a full flag, it's a partial flag of sub-representations. So the wi's should be fixed by the x gamma and x gamma star. But we also require that one of the x gamma acts nilpotently and acts by 0 on the quotient. Okay, so this is what we define as semi-nilpotent representation. And let us denote by lambda v the closed substack of semi-nilpotent representations. So this condition is especially important when you have edge loops. So if you consider just plainly nilpotent representations, when you have edge loops, it's easy to see that you will never get something Lagrangian. And so this is a theorem due to Tristan Bozek a few years ago that this is a Lagrangian substack. So here, the subtle point, I'm guessing this is for people who are really, really following. Here, I didn't specify what are the possible dimension jumps. And actually, this makes a difference. So if you require the dimension jumps to be supported at a single vertex or not, it makes a difference, especially when you have oriented cycles. So you will actually have two versions of this lambda v. And they might and would disagree when you have oriented cycles in your quiver. This is just a subtle point. Let's not worry too much about it. Okay, let's give examples of these Lagrangian correspondences and why, at least in this example, you can see that they're nice and Lagrangian. Let's just look again at this Jordan quiver. Then what we have in this case is easy to see. It is inside this commuting variety. We have the pairs of matrices such that one of them is nilpotent. That's all. And this is a disjoint union of conormal bundles to the nilpotent orbits, so it is definitely Lagrangian. Irreducible components are parameterized by partitions. Now let's look at SG. When G is greater than 1, then irreducible components are not parameterized by partitions anymore, but by compositions. And here is one special, well, maybe nicer strata, irreducible components, corresponding to the trivial composition, and it is just when x is 0 and the x stars are allowed to be anything. They don't necessarily preserve a flag, a non-trivial flag. Okay, this is a closed, this is an irreducible component in this Lagrangian lambda v. Okay, these are just examples. And so here's the main theorem, I would say, the first main theorem. So we can define, just as before, we can define the cohomological Hall algebra, but using these Lagrangian correspondences instead of the full representation of the pre-projective algebra. So this is exactly like in the case of operators acting on the homology of this moduli space of instantons. We require that the points that we add are on the line. Okay, we have chosen a line because we have a splitting of the set of arrows in the doubled arrows, in the doubled quiver, and we require essentially support along this line. Okay, so just as before, this is an algebra. It acts on the moduli space. It acts on the homology of the Nakajima quiver varieties. And here are some results on this algebra. So the first two, at least the first one is technical. Let me just leave the mathematicians in the audience, they can read this. Since I am only at number 10 out of many, let me just mention or focus on the 2 and 3. So 2 says that this algebra acts faithfully. All right, I sum over all v's and w's. Maybe it's enough to sum over v and take some suitable w, I don't know. But anyway, it acts faithfully on this sum. And the important result is that we have a family of generators for these algebras. So it is generated by certain very simple fundamental classes. So we take all vertices which do not have edge loops, and we take the one-dimensional representation of the pre-projective algebra at that loop, and this is just a point, and we take the fundamental class of that point. Not very impressive. And for imaginary vertices, now we have to do something a bit more complicated. For any positive integer L, we have this Lagrangian correspondence, which I had described before, which is, if you want, the zero section. If you view this as a cotangent bundle of something, this is a zero section. And this COHA is generated by these guys. So even when you don't have any imaginary root, this is an interesting result. It tells you that whatever complicated algebra you get, well, it's going to be generated just by the same guys as before, the Nakajima operators. These are Nakajima operators, actioned by the fundamental classes here. They are the original Nakajima operators. It means that the equivariant cohomology has a pure mixed Hut structure. This is not true if you forget equivariantly. It's not true that it has a pure mixed structure, but equivariant pure. Okay, and because of this torsion freeness here, we can use a standard trick. We localize at the fixed point of this torus, and we will get explicit combinatorial realization as a shuffle algebra. So some people, especially Andrei Negut, are very good at using such combinatorial realizations. And, well, this is going to be more complicated in general than for the S1 quiver, but still, in principle, it's possible. Okay, so now what do we have? We have generators for this COHA. And, okay, this is nice, but we would like to know a bit more about the intrinsic structure of this algebra. So one thing that we can do is that we can compute the character of C lambda. We can also do it for C, but it's nicer for C lambda. And as we will see, the answer is given in terms of Katz polynomials. So I have to remind you first, what is a Katz polynomial? Katz polynomials are a family of polynomials associated to any quiver, arbitrary quiver, defined by Katz in the early 80s. And they have been known to play a very important role, at least their constant term, and be very strongly related to Katz-Moody algebras. And so let me recall the definition. For any finite field FQ, now we consider representations of our quiver over the finite field FQ, and we count the isomorphism classes of indecomposable representations, which remain indecomposable if we tensor by the field by the algebraic closure of FQ. So these are the so-called absolutely indecomposable. And so we fix the dimension vector, and we count the number of isomorphism classes of representations, which are absolutely indecomposable. And the first theorem of Katz says that this is actually a polynomial in the size of the finite field. This is not at all obvious, because there is no nice algebraic variety which parameterizes the isomorphism classes of absolutely indecomposable. It's only constructible, and it's a stack. And here you're not counting the volume as a stack. You're really counting the number of isomorphism classes. So it's not obvious at all that it is a polynomial, but it is true. And I said that to an equiver Q, you want to associate a Katz-Moody algebra. So how do you do that? Old recipe, of course. You forget about the arrows. You have the underlying graph. And you consider the Borchardt-Katz-Moody algebra associated to that underlying graph, which we view as the generalized Dynkin diagram of this Borchardt-Katz-Moody algebra. And so this Katz polynomial is non-zero only when V corresponds to a root of that Katz-Moody algebra. Okay, and this Katz polynomial was recently shown by these three people to be a positive coefficient. Okay, let's give some examples. If Q is a finite Dynkin, then this is 1. If you're a root and 0 otherwise. If Q is affine Dynkin or S1, then this is 1 if you are in a real root, and T plus the rank if you are an imaginary root, and 0 otherwise. So here we start to see that these polynomials are not constant. They're actually polynomials. So S1 case, it's always equal to T for all V. And let me just give one example that you can see it can get a bit ugly. If you take a SG quiver, then you look at dimension 3, you get something like this. Okay, so let me be very, very brief about this. Very, very brief about this. Hua gave an explicit formula, and here is the formula. You can see it looks a bit like a I don't know, denominator formula for dimension of for the character of enveloping algebra of a Lie algebra. Okay. All right. So it turns out that these Katz polynomials are not quite the ones we want in order to understand the cohomological Hall algebra, this Lagrangian cohomological Hall algebra. And we need some variant of these Katz polynomials. So this will be different when we have edge loops. And we say representation is edge nilpotent if whenever you have a loop, imaginary vertex, you have loops at the vertex I, then all the arrows associated to that vertex are simultaneously nilpotent. Okay, this is just a definition. And you can show that there is a unique polynomial which counts these as well. So it's better behaved, and it has the same, it will be positive coefficient, although we haven't proved it yet, but there's no doubt it's going to be positive coefficient. And if you look at this, it just means the sum of the coefficients are equal. So it's just a reshuffling of the degrees, but the monomials somehow are the same. So here are some examples. Well, as I said, if you have no edge loops, then it doesn't change anything. If Q is this Jordan quiver, then we have 1. So we don't have a T, but we have 1. At least there's a non-zero constant term. And you see that if Q is SG, then it looks a bit better than the one we had before. Okay, it's a bit better behaved. And, okay, you can give a formula like Hua, and you can replace this semi-nilpotency condition by the other semi-nilpotency condition, which is different when you have cycles. This was the little subtle point before, and this will amount to replacing this edge nilpotency condition by a standard nilpotency condition. Okay, let me not waste too much time on this. But this is the result which I wanted to get to. So the Poincaré polynomial of this Lagrangian stack, lambda v, is actually encoded by these nilpotent Katz polynomials. So let me comment a bit on this equality. So it says that if you want to compute, so if you says, it says that the Poincaré polynomial of lambda v, the generating series for the Poincaré polynomial, suitably shifted of these Lagrangian stack, is the same as the Poincaré polynomial of a Lie algebra, or more precisely, of the current of a Lie algebra, which would have a character given by these nilpotent Katz polynomial. So before I say more about this, let me just make some observation. How do we prove this? We prove this by counting, but more importantly, we compactify lambda v in terms of Nakajima quiver varieties, and then we use Hausel's work, which gave a formula for the Betti numbers of Nakajima quiver varieties. So there is some work to get from here to Hausel's theorem, but then you really need Hausel's theorem that computes the cohomology of this Nakajima quiver variety to reach such a formula. And so let me make more precise what I said just a few minutes ago. Let's go back to this equation. So you see that here what is important is the Poincaré dual of this polynomial counting, is a Poincaré dual of the polynomial counting nilpotent representations. So if I take the leading term, i.e. the constant term, in T, in this equality, this is going to be equality of series in T power minus 1. And Laurent series in T minus 1. So if we look at the constant term, then we get something like this. We only get the top dimensional homology group. And we only get the constant term of the nilpotent Katz polynomial. This is just by taking the leading term. And, well, what does this mean? It means that these top dimensional homology, which is known by work of Bozek to be isomorphic as a graded vector space to the enveloping algebra of a certain Lie algebra associated to the quiver, which is, this is not a typo, this is really the Bozek-Kac-Moody algebra, something a bit bigger than the Borchardt-Kac-Moody algebra. So there is a certain Lie algebra, which is slightly bigger than the Borchardt-Kac-Moody algebra, whose graded dimension is given by the constant term of this nilpotent Katz polynomial. And, right, so from this equality, we get exactly that the character of this Bozek-Kac-Moody algebra is given by the constant term of this Katz polynomial, this nilpotent Katz polynomial. And this is new only in the case when you don't have edge loops. Otherwise, this is just Katz conjecture, and it was proved in 2006 by Tamas Hausel. So it's an extension of these two arbitrary quivers. But this is just the leading term of this computation of the Betti numbers, if you want, of these Lagrangian correspondences. And so the full guy is going also to be the character of a certain now graded Lie algebra. And so, okay, how to make this a bit more precise? Unfortunately, at the moment, we do not know, unlike this Molekov-Kunkov-Yangian, we do not know that our cohomological Hall algebra is the enveloping algebra or a deformed enveloping algebra of the current algebra of a certain Lie algebra. This, at the moment, we don't know. Hopefully, we can use some arguments about the existence of a coproduct on these COHA to deduce this. But for the moment, we don't know this. But if we assume, as is surely going to be the case, that this Lagrangian COHA is a deformation of the enveloping algebra of a Lie algebra, then this equality shows precisely that on top of this, say, Bozek-Kac-Moody algebra associated to the quiver, we have a larger algebra, a graded Lie algebra. It's going to be graded. And the degree 0 piece will be the previous Lie algebra, this Bozek-Kac-Moody algebra. But there is a larger one which is graded, and its graded dimension is given by this nilpotent Katz polynomial. So, yes, before we had an interpretation of the constant term, and now if this is indeed a deformation of the enveloping algebra of Lie algebra, then that Lie algebra is the decurrent version of that Lie algebra has this as a character, has the nilpotent Katz polynomial as a character. Okay, so why were we looking for this? Well, we were trying to prove a conjecture of Okounkov, which made exactly this conjecture in the case of the Yangian. Okay, so, but since we don't know precisely the relation between our C lambda and this Yangian, at the moment we cannot hope to understand the dimension of this Molekov-Kunkov-Yangian. Okay, this was with regards to the dimension of this COHA, the character of the COHA. Now let's try to guess what the actual COHA could be, what the actual Lie algebra could be, this strange Lie algebra. What could it maybe be? So it turns out that just the same kind of formulas appear in a slightly different context. So context is the following. We are over a finite field, and we consider the moduli stack of representation of the quiver over that finite field. And this is not the doubled quiver. This is just a quiver. And we have an algebra structure on, we could take the homology, but let's take the space of functions. This is the most down-to-earth version of whole algebra you can think of. So we take the space of functions on the stack of representation of the quiver, and there's an algebra structure called the usual whole algebra. It's a tautology that the dimension of this whole algebra is given by this formula. So it is a platistic exponential in this Katz polynomials. This is just because this algebra is a space of functions, and the number of points on the space is essentially given by the Katz polynomials. Okay, this is nothing deep here. And I hope they're not watching, but there is nothing too deep here either. But it's a very nice result. So if you look at this whole algebra, one can show that this is a self-dual Hopf algebra. So it carries a certain, it's a Hopf algebra, and it carries a certain Hopf pairing, which is non-degenerate. And in these cases, you have a good chance of being a Borchertz-Kac-Moody algebra, or rather a quantized enveloping algebra of some Borchertz-Kac-Moody algebra. So notice that Kac-Moody algebra definitely depends on FQ, right? So just the dimensions of these guys will depend on Q. Okay. So and how do you construct the Borchertz-Cartan datum? So it's going to be a huge Borchertz-Cartan datum. Well, you have to consider all the so-called cuspidal elements in your whole algebra, and look at the dimensions of the spaces of cuspidal elements. So what is a cuspidal element? This space H cusp FQV. This is just the space, the vector space of primitive or quasi-primitive elements in the whole algebra. And if you are primitive, you cannot be generated by guys in lower dimension. So this big algebra needs these cuspidal elements as generators. It's a very standard context. And so the Borchertz-Cartan datum is given by essentially the dimension of these spaces. Okay, one can show that the dimension of these spaces are polynomials with rational coefficients, not integer, rational coefficients, in the dimension of, in the size of the finite field. Okay. So if we compare to the situation that we had before, what we could naively hope is that this kind of mysterious algebra whose Yangian is isomorphic to the COHA looks like a graded version of a Borchertz-Kac-Moody algebra whose Borchertz-Cartan datum would be somehow encoded by the collection of all these polynomials. So I don't have a precise conjecture to make here. All I can say is that in the affine case, you can make this work because you can compute everything. And there's something a bit subtle here, because if you look at this formula on this side, T stands for a grading on the algebra. T is just a grading on this algebra. Whereas in this case here, never mind the fact that this is not the nilpotent Katz polynomial, it doesn't matter. But here, Q is the number of points in the finite field, and here Q is the dimension. I mean, this is the dimension of the space of functions. The dimension is a function of Q. Okay, it's not that there is a grading or anything. It's just the dimension of your spaces are polynomials in Q. So there is some kind of trick, algebraic trick, that you definitely need to do. But at least in the affine case, you can define polynomials that will turn out to be positive coefficient. Using this kind of trick, you somehow, yes, I don't know how to say, you mess up a bit with these polynomials so that they become positive integer coefficient. And then you can check that this algebra, whose Yangian is the COHA, is actually the graded Borchertz-Kac-Moody algebra with this data. So this KV of T is the multiplicity of the simple imaginary roots that you need to add to your original set of simple roots in your quiver to get the full algebra G bar Q. Okay, what's next? I have no idea. I forgot. Okay, now we go a bit crazy. So we leave quivers. We leave the word of quivers, and we go to curves. So this is one of the games that people have been playing, including myself, for many years now. I think it started with Kapranov 20 years ago, making some nice observation about whole algebras of curves. So whatever you do with quivers, you can try to do with curves. And especially, so you would replace the category of representation of your quiver, which is a category of homological dimension 1. So every object has a length 2 projective resolution. You can replace it by the category of coherent sheaves on a smooth projective curve, which satisfies the same property, homological dimension 1. And in this case, this stack, lambda v, nilpotent stack, is straightforwardly replaced by this moduli stack of nilpotent Higgs sheaves on your curve. And here I really want the stack of nilpotent Higgs sheaves. You should not try to make a moduli space out of this. It's just a stack. Okay, and so you can define an algebra structure on the homology of these stacks. Here the C star is the only thing that we are left with in the case of curves, at least in an obvious way, which is just the action on the fibers of, so on the Higgs field. This is the action on the Higgs field, dilation on the Higgs field. So there's an algebra structure on this guy. You can do the same thing for the K theory. And of course, it would be great to compute these. But even in the case of P1, this is not so easy. In the case of P1, we have an extra C star action because this is the one curve which admits a C star action. And so here's the conjecture that the at least K-theoretical whole algebra of P1 with this two-dimensional torus should be given by a quantum group, quantum toroidal GL2. And if you think about K of P1, it definitely contains a category of nilpotent Higgs sheaves, nilpotent Higgs torsion sheaves supported at 0 and infinity. And it's easy to see that the nilpotent torsion Higgs sheaf supported at a point is the same thing as the coherent sheaf on C2 supported at a point. And so if I just look at torsion sheaves here, just torsion sheaves, then I will already have 2 copies of the Yangian of GL1 hat in the COHA, or 2 copies of the quantum toroidal GL1 hat in the KHA. And so the claim is that these glue together, and if you consider also higher rank Higgs bundles, then you will get actually GL2 toroidal. Okay, this is just a conjecture. And you can make similar conjectures for orbifold P1s, where we put some orbifold structures at the points 0 and infinity, and then we would get a quantum toroidal GLK or quantum toroidal GLA plus B. Okay, so why would we like to consider this kind of cohomological Hall algebra or K-theoretical Hall algebra? It's because we want to act on some homology or K-theory of some actual moduli spaces of sheaves. So one place where we can do it is the following. We consider resolution of the Kleinian singularity of type A, and we consider the moduli space of framed torsion-free sheaves on a suitable compactification. So this is somehow like the Nakajima, like the moduli space of framed instantons, except that it is, again, a Nakajima quiver variety, but with a non-dominant stability parameter. So the work of Nakajima cannot be applied directly to these guys. Of course, they are diffeomorphic, but it cannot be applied directly. So any irreducible component has self-intersection -2. And so if you look at coherent sheaves on the surface supported on these components, this is just a nilpotent Higgs bundle, nilpotent Higgs sheaf on P1. And so there's an action like this. an action of this K-theoretical Hall algebra of P1. And you will get the same thing in all cases where you have a P1 inside the surface with self-intersection -2. If you have an actual nice moduli space of torsion-free sheaves on that variety, on that surface, then you can hope to get an action of these UQ-GL2 toroidal. And we guess that all these actions for the different irreducible components should produce the expected action of the quantum toroidal GLK on this equivariant K theory. This is known by work of Nakajima, and before that, Varaniolo and Vasro, in the case of a dominant stability parameter. But here, somehow, the positive half will be very different, the generators will be very different, and the moduli space is algebraically different. Okay, so we can try to do this in a more general context, as I said. And let me just finish with the next step. Naturally, we want to understand this K-theoretical Hall algebra of Higgs sheaves. And this, I think, should be an interesting object. So let me state a result that I proved last year. So these Katz polynomial counting indecomposable, absolutely indecomposable representation of a quiver, they also exist in the context of curves. One more minute. They also exist in the context of curves. And now they are polynomials, but in the set of Weyl numbers of the curve. So we have 2G Weyl numbers associated to your curve over your finite field, satisfying some properties. And this is a polynomial in these 2G Weyl numbers. And now I would like to say that the cohomology or the moduli stack of Higgs sheaves is given by generating functions involving these Katz polynomials. This will be true, except that it is meaningless because everything diverges. This is one nice or nasty, depending on your taste, fact about the nilpotent Higgs sheaves. If you look at the stack, then the cohomology is infinite dimensional in any reasonable degree. And, but nevertheless, you have such a result for the stable nilpotent moduli space of stable nilpotent Higgs sheaves is given by this Katz polynomial, or the Poincaré dual. And what this really suggests is that if you look at the cohomological Hall algebra of that nilpotent Higgs sheaves, then you would get the Yangian of certain Lie algebra whose graded dimension vector would be given by these Katz polynomials of curves. And my favorite curve is, of course, the elliptic curve. That's the Jordan quiver. And if G equals 1, then what you would expect is that this Lie algebra itself should be GL1 toroidal. And so the Yangian of GL1 toroidal is a triple loop algebra. And this just reminds me of my postdoc with Igor Frankel at Yale, where for 2 years he told me that I should be looking for elliptic Lie algebras. And after I found some, in certain cases, 2 years later, he told me that I should forget about elliptic Lie algebra, and the thing of the future was this triple loop algebras. So 15 years later, I have one in sight, but it might take 15 more years to actually get my hold on this. But and with this, I will finish 2 minutes late. Sorry.
Thank you. Quick question. Oh, 2 quick questions. Greg. Greg was first. Oh. Mathematicians again. They always snatch things from physicists.
All right. So then I have 2 questions.
No, just one.
So
just
one is a short one. Why you work with finite fields, not with modules? What prevents you to do the same?
Well, to prove the existence of these Katz polynomials, of these cuspidal, you mean in the case of counting cuspidal functions, cuspidal elements?
Katz polynomials.
So in the case of the polynomial counting cuspidal functions, I use, or Tristan and I use this Borchardt-Kac-Moody formula to get this Borchardt-Weil character formula, so that we iteratively compute the number of elements in the Borchardt-Kac-Moody algebra up to a certain degree. And then we know what is the graded dimension of the full Hall algebra, so recursively we can compute these polynomials. And I don't see how to do this motivically.
Okay. Yeah, and the second question is, next slide, okay.
Okay, I'll try to make this quick. So the cohomological Hall algebra doesn't depend on a stability condition for the quiver, right?
That's right.
Right. So one way to try and apply your results to physics is to take the super quantum mechanics associated with the quiver. And then it can't be the algebra of BPS states because the spectrum of BPS states famously depends on a stability condition. But it does have a physical interpretation, probably, in terms of supersymmetric, the algebra of supersymmetric operators in the super quantum mechanics. And that's something I started to work out with Dima Galahoff. And the algebra of BPS states is something entirely different, where you take L2 harmonic waveforms, multiply them, and then project onto an L2 harmonic waveform.
Okay. I knew it was coming.
Well, let's thank the speaker. So the next talk is by Misha Bernstein, who will speak about plane partitions and W algebras, unless he changed his title.